Hello, everyone. Welcome to the ILTA Physics online problem-solving lecture. Today, we are going to study problems related to friction. Friction is a hidden force that opposes the motion of an object. However, it doesn't just get in the way. It actually plays a very important role in helping objects also move in our daily lives. As you can see in the image below, the reason we can walk on the floor is that friction exists between our shoes and the ground. Just think about how hard it is to walk on a smooth ice rink where there is almost no friction, and you'll realize how essential friction is for motion. Friction problems are mainly divided into two types: static friction, where an object stays put, and kinetic friction, where an object is accelerating or moving. Let's start by summarizing the basics of friction. Friction can be broadly classified into static friction and kinetic friction. First, static friction is the force that prevents an object from slipping, acting between the object and the surface. This force always appears in the opposite direction of the intended motion and exists parallel to the surface. What's interesting is that the magnitude of static friction is determined by exactly balancing the force applied to the object. Because the applied force and the friction force have the same magnitude but opposite directions, the net force on the object becomes zero and the object does not move. If you push an object and it doesn't budge, the static friction at that moment is exactly equal to the force you are pushing with. However, there is a limit to this static friction, which we call the maximum static friction. It can be calculated by multiplying the coefficient of static friction by the normal force. Next, kinetic friction is the friction that acts when an object is sliding across a surface. This force also acts in the opposite direction of motion. However, unlike static friction, kinetic friction is not always equal to the applied force. The magnitude of kinetic friction is proportional to the normal force and is determined as a constant value by multiplying the coefficient of kinetic friction by the normal force. Therefore, if we push an object with a force greater than the kinetic friction, the object will accelerate and slide with a force equal to that difference, even though friction is present. An interesting fact is that kinetic friction only depends on the normal force and has nothing to do with the speed of the object. Also, kinetic friction is usually smaller than static friction. This is why it generally takes less force to keep an object moving at a constant speed once it starts moving than it does to get it moving in the first place. Now, let's solve some basic friction problems. In problem 24, let's look at a situation where a mountain goat is standing on a cliff without slipping. A goat weighing 900 newtons is standing on a very steep cliff with a 60-degree angle from the horizontal. We need to find the normal force and the static friction acting on the goat. For motion on an incline, it's always convenient to break the forces into components perpendicular to the slope and parallel to the slope. Let's look at the free body diagram on the right. The weight of the goat is being applied vertically downward due to gravity. This downward weight can be divided into a component perpendicular to the slope and a component parallel to the slope. If the goat standing on the slope is stationary and not slipping, the component of the goat's weight perpendicular to the slope and the normal force acting on the goat remain equal. Also, the parallel component of the weight matches the magnitude of the static friction acting in the opposite direction. I hope you clearly understand that static friction has the same magnitude and opposite direction as the force applied to the object. Now let's calculate each component. Since the weight is 900 newtons, if we use trigonometric properties, normal force equals weight times cosine 60 degrees equals 450 newtons, acting perpendicular to the slope. The force acting parallel to the slope that tries to pull the goat down is the force that balances with the static friction. static friction equals weight times sine 60 degrees equals approximately 779 newtons. Since the goat is standing without slipping, you can understand it as a friction force of the same magnitude as the downward pull of gravity acting in the opposite direction. Problem 26 is about a box sliding on the floor. Let's assume a box stops after sliding a certain distance based on its initial velocity at the moment the pushing force disappears. Friction opposes the motion and brings the box to a halt. The question asks how the sliding distance changes if the mass of the box is doubled, or if the initial velocity is doubled. From the problem description, after the pushing force is gone, the only horizontal force acting on the object is kinetic friction. And remember, kinetic friction is only proportional to the normal force of the object. First, after reading the problem, you should be able to draw a diagram of the box's motion like the one on the right. Of course, it's essential to first define the coordinate system and the origin to describe the motion. The drawing shows the box sliding to the right with an initial velocity, moving a distance d, and then stopping. What's important here is to correctly understand the direction of the acceleration that reduces the speed. Since we set the movement to the right, please note that the direction of the acceleration stopping the box is to the left. This kind of drawing is a kinematic diagram representing velocity, acceleration, and distance. Now let's draw a free body diagram considering all the forces acting on the object at any moment while it's moving. For the object sliding to the right, the forces acting are the weight pointing down, the normal force pointing up, and the kinetic friction acting in the opposite direction of motion, which is to the left. You don't necessarily have to draw elements other than forces in a free body diagram, but you can include the direction of velocity to help with understanding. It's important to practice drawing both the kinematic diagram and the free body diagram accurately. Now let's organize the equations of motion using the given conditions. First, kinetic friction can be expressed as the product of the coefficient of kinetic friction and the normal force. Since the normal force has the same magnitude as the weight, the formula is as follows. Kinetic friction equal mu sub k times mass times g. This means the frictional acceleration created by kinetic friction is calculated as the product of the coefficient of kinetic friction and the acceleration due to gravity. Now let's calculate the displacement. Based on the acceleration, we can use the relationship between velocity and displacement, which is used when there is no time information. V squared equal V naught squared plus 2 times a times d. Since the final velocity is 0, if we rearrange the equation as follows. Note that there is a minus sign in the equation. Here, since the frictional acceleration is opposite to the direction of motion, it has a negative value. Looking at the first question where the mass is doubled, we can see that the sliding distance has nothing to do with mass. In other words, even if the mass changes, if the starting velocity is the same, the distance traveled until it stops is the same. However, as in the second question, if the initial velocity is doubled, the sliding distance increases 4 times due to the squared relationship in the distance formula. This problem itself isn't difficult to calculate, but please practice the ability to understand motion kinematically and describe forces accurately through free body diagrams. That's it for today's lecture. Great job, everyone. I'll see you next time.